Good morning. Let us have a today class on drag and lift, which is the last class of this course. Okay, that's lecture number 36 and drag and lift. I think discussion of the drag and lift I started from the lecture number 2, where we illustrated how we can estimate it, what will be the drag and lift forces of the towers, the way. And also we talk about this, how the bars drag and lift forces in linear momentum equations. So, if you look at that, we have really remarkably progressed in experimental fluid mechanics, or we talk about wind tunnel testings or water flow testings, as well as we also remarkably improved in numerical experiments using computational fluid dynamics softwares, as we demonstrated many cases. So, if you look at that, to really design a fuel efficient car, or you talk about design a wind turbine, all it needs a informations knowledge on this drag and the lift, which actually help us to generate wind powers from wind tunnel. So, if you look at that way, I am not going more details. I am to encourage you, just look at the very good illustrations are there, and in the book of Sembala, which gives you a lot of interest on the fluid mechanics. If you look at the illustrations what is provided in a Sembala book. But today I will be very briefly, I will talk about the slip, drag and lift, and frictions and pressure drags, drag coefficients of common geometry, and we will have a parallel flow over the flat plates, which already we discussed in boundary layers concept. That is the same concept we will talk about. Now, if you look at that, take a simple examples. Okay, when you have a cyclist, okay, driving a bicycles, okay, if you can look at recent Olympics and all, if you see these persons leans it, okay, as to reduce the drag forces, it just leans it as going with so the basically minimizing the drag force. So, it leans up depending upon the speeds, and you can see that the bicycles what is designed for the low velocity and the racing bicycles are the different. And more often, if you look at the cyclist, how it changes to reduce the drag forces, drag forces, okay, which is acting in the directions of the flow. So, in direction of the flow, because of air resistance, because of the flow structures, all it's create a edge equivalent to a drag force. So, most often we define the drag force is a functions of half rho v squares is a dynamic pressures, as we discussed earlier, multiplied with a CD, this is called coefficients of drag, into A is the frontal area, A is the frontal area. So, the basically these coefficient drags we can get it from experiment, basically conducting wind tunnel test, or we can do numerical experiment. We can do the numerical experiments to estimate what will be the CD value, okay, or we can do a wind tunnel physical experiments to estimate the CD, because CD is a functions of velocity, functions of rho, density of the fluid. It depends upon the velocity, which we can say that is a pre-stream velocities, and it also depends upon the frontal area, the shape, size and orientations. So, the basically a cyclist who participates like very competitive racings like Olympics and all, he tried to reduce this A value, he will try to reduce this A value or will be try to reduce this CD value. That is two things, he can reduce it, so that drag force will be the minimum and he can increase the velocity. That is the availability for any cyclist or the racers in any competitive racing things. He can practice so well that he can reduce these frontal areas. That is what he will have a the clothes fitting dress and such a way that, so the frontal area he can reduce it, he can lean such a way that it will reduce the frontal area, as well as it has to look at what is the shape and size, the orientations, based on that CD varies. So, if you look at any cyclist which is really participating like national or international games, he try to do level best to reduce the frontal area and reduce this coefficients drag, so that he can increase the velocity with the same force, he can increase the velocity. So, if you have a very simple examples that if I do not have the CD variations, okay, if you have a upright positions, okay, just driving like this, okay, the CD value will be about 1.1, and if you have this CD value can goes, if you just bend it, the CD goes to almost 20% slower. That is what it happens, it almost the 20% slower. So, we get it the CD just you bend it. So, that is the basic idea how the research does it. Same way, if I give a very simple examples like there is a half disc, and if this flow is coming like this, if this velocity v, disc having the diameter d, if I have the half disc as close to a umbrella. Okay. So, if you have the velocity v and half disc, as you can understand how the flow turbulence structures will happen, how the boundary layer formations are there. We are not going to detail about that. We are just looking at how the flow separations happening. All details we are not going it, because this type of shape with a velocity v, we can conduct internal test or the numerical experiment using computational fluid dynamics softwares. So, if you do it, you will get a CD value is equal to 0.4, 0.4. That is what the CD value. If you have the velocity like this, and you have a high semicircles, and not going details, which okay, it is considered the Reynolds numbers greater than 10 to the power 4 in the turbulent regions. So, we have the CD value is equal to 0.4. But same things if I can just reverse it, like you do it sometimes your umbrella, okay, the wind directions and your umbrella directions will be different. In that case, the CDs will go to almost 3 times of this value 1.2. That means, the drag force is exerted when you have parallel your umbrella with the velocity. That is what will be 0.4 times of half rho v square into A, okay, dynamic pressures n A, but same umbrella if I just hold it differently. So, the force because of these orientations, this force will be, if I put the dash, it is a 3 times of the FD force. That is what you can experience it when you try to do a normal case when you have a raining, how to handle the umbrellas. Okay. That is the way you change the drag forces, which is almost a 3 times higher. Okay. With a CD is 0.4 to 1.2. there are number of examples. Okay. You can really see in the real life conditions how the drag and lift is playing the roles for us when any external bodies flow past over a bodies or flow past over a bodies. You can see that how the drag force and lift force are working it, and how we can change the drag force and lift force, which very simple way it's defined as a CD. The coefficients of drags will, more details will come, which will be the, is nothing else force of drag divided by dynamic pressures, rho v square is a, rho is a density into the frontal area, okay, as equivalent to the force due to the dynamic pressures. That ratios is equal to the coefficients of drag coefficient. That is what you can have. So, simple way the examples what you have given it here, as you know it, nowadays we have been implementing series of wind turbines. So, wind turbine to harvest the wind energy. So, if you look at if you have this velocity v is coming it, how to design this belt, okay, such a way that will be high powers will get it. Okay. So, if you look at very smaller area, it's just like a wing, the aircraft wings, you have a drag and lift. Because of these drag and lift forces, this is what goes to rotating it. Okay. So, more details you can understand it in higher classes, but if you look at the wind turbines, you can talk about the cyclist, we talk about swimmers, or you talk about any gymnastics. Okay. If you just look at the beautiful part of the gymnastics, that he or she trains himself with a lift and drag force such a way that he knows that how to change the body shapes and also the wind speed such a way that he can really perform the gymnastics very well. Same way if you look at the in crickets, when you somebody's spinners or the bouncers, they are throwing the balls, and all these interactions you can understand it with these lift and drags. So, it is a very interesting subject, but as we have very limited time of finishing this course in this class. So, let us talk about drag and lift, friction and pressure drags, okay, which is in definitions wise how the drag coefficients are common geometry, as I just given some examples of and parallel flow over the plate, flat plate, which is the boundary layers. And then you will solve a very few examples on how to solve these real life problems using this lift and drag concept. Now, if you look at the drag, okay, which is it is a very simple definitions, as you can understand it, that is a force flowing fluid exerted on a body in the flow direction is called the drag. Okay. Just normal to that components, we can say that is the lift. Okay. So, if in a flow directions, okay, this is the flow directions. In these directions, if there will be a force acting this because of the boundary layer formations, because of the pressure difference, all details we are not going it, which we already discussed in boundary layer concept. If I have a small aerofoils, so where we can compute the drag forces, okay, which will be the force of flowing fluid exerted on a body in the flow direction is called drag force. Just perpendicular of that force is the lift force, that is what the lift force. So, you have a lift force, you have a drag force. So, as you know it, how the boundary layer formations happens, how the flow separations happens, all we discuss in the class in boundary layers. The component of the pressures and the wall strips in the direction normal to the flow tend to move the body in that directions, their sum is called the lift. Now, if you look at these cases, okay, if I consider aerofoils, and I have the free stream velocity is coming like this. If you know it, there will be boundary layer formations and there will be the pressure difference will be generated. So, if I take a small area dA, if I take a small area dA and for that area I have a wall shear stress tau w into dA will be the force components, and I have the pressures which is acting on P into this is a pressure force, okay. And I have the normal components, and that is what I can look at that it is making a theta degree angles, okay. It is making a theta degree angles, okay, at this normal component with the components of the horizontal directions, the flow directions is making a theta degree angles. So, if you can see that as you discuss in the boundary layers, there will be a generations of boundary layers, the flow separations and boundary layer thickness, okay, which generate the wall stresses variations, okay. And we are not going details, we are just looking it, and this also have the pressures. So, if I have the pressure field, if I know this wall shear stress with a very simple force component resolutions, okay, just computing the component in these directions as well as the perpendicular this. So, this direction is a drag force direction, this is the force direction is a lift force direction. So, two dimensional flow, the resultant of the pressures and shear force can be split in two components, one in the direction of the flow which is the drag force, another in the directions of normal flow which is the lift. That is what I repeatedly saying these things. But if you generally we have three dimensional structures where is a side force component also comes normal to the page, normal to this blackboard to move body in that direction. So, anyway we are not discussing how three dimensional flow happens in these course curriculums. So, if I look at the drag force and lift force, it is a simple things now for us, because we take a small area dA, we estimate the force because of wall shear stress and the pressures, and if I resolve it these components in terms of the drag force for a element of dA, small element of the dA, I will get it the force component P dA cos theta, negative signs because it is opposite of this flow velocity line, and you have the force components due to the wall's shear stress. That is what we will get it for the lift and the drags. This is coming that if I know it from any experimental studies, if I can measure the pressure as well as can measure the shear stress, I can also compute it what is the drag force of each small elements of this surface. For each element of the surface I can estimate it, it is not a big issue, okay. If I have a conducting this experiment in the wind tunnel, or if I conduct in a numerical experiments like computational fluid dynamics, I can get the pressure field, I can get the velocity field. From that velocity and pressure field, I can estimate it what will be the wall shear stress, okay. Also some of the CFD softwares also gives the wall shear stress. So, as you know this wall shear stress, you can just integrated this part to understand is total force, integrating these equations entire surface, okay, you will get the drag force and the lift force, okay. That means the drag and lift force is varying with a smaller dA of the surface area, we are just integrating it, which is very simple things. But most often as I said that for engineering applications or designing experiment conditions, we simplify the things, we do not go for very complexity, because we conduct the wind tunnels, we conduct the numerical experiment. End of the day we give a chart of the coefficient of drag and or the drag coefficients, or we talk about the lift coefficient. So, because that will be easier for engineers to implement it, to understand it, how the better design should be there. For examples, like you have a tall buildings, okay. You have a tall buildings, okay. You want to design the wind speed, maybe as we have given the example of the same things in very beginning of the classes of if there is a cyclones having around 200 kilometers per hour, okay, and we can have a two type of platforms we can have. One is the platform of these tall buildings could be around more than, let be 50 meters high, and you consider the wind speed of 200 kilometer per hour as close to a cyclone, whether the building footprint or the plan of the building should be square or the circular to reduce the drag force. That means basically reduce the CD value. So, we can look at this elementary geometry and you can understand it, that which one will give a minimum CD values. That is what you can understand it. It's not from just graphically you can say. So, that is the reasons we conduct a series of experiments and we finally we provide the CD values, which is the guideline for a engineer to decide it when you constructing a high rise building. High rise building, he has to look at whether he has to go for this shape, rectangular shapes or a circular shape. That is a very simple CD values, and if you can interpret it that how these CD values variations are there and which one will be the more, just think about that. So, that means we can define it a very simple way. The coefficient of lift and the drag coefficients is a functions of, because if you know the CD value, you can estimate the drag force half by rho v square into A. Okay. A is the frontal area. That means, for this case my frontal area is B and if is the length L. So, the frontal area is A, frontal area is B into H. That is what is my frontal area. A will be the, but in this case I have the diameter D and length, the frontal areas will be D times of L. That means you are looking this, what is the projections in the just looking from the velocity sides, flow velocity directions, what is the projections? That the projections is the frontal area. So, if you look it for the circular case, you have a frontal area D into L, but in case of a rectangular case in the B, so you know the frontal area. So, you know the frontal area, you know this CD value, you know the design velocity, you can always compute it what will be the drag force. Is a very simple thing. Same way we also make it the lift force is a very simple way. CL FL is a lift force divided by same functions rho v square into A. Okay. So, these drag and lift coefficients are primarily functions of the shape of the body, as I said it. It also depends upon the Reynolds numbers and the surface roughness. Okay. That is also matters it. Okay. What type of buildings we have? Okay. If you have a new constructions building versus old buildings. So, definitely the CD will be the different, the roughness will be the different. That is the difference. Okay. If you look at that, how is it a new buildings or any type of roughness we are creating, because that what is matters us, and also the flow Reynolds numbers. That is what we will be discussing, that the CD also have a functions of velocity, rho, frontal area, also the Reynolds numbers and roughness, as similar to we discuss about the roughness for pipe flow. That's similar concepts. We have the roughness. I am not going more detailed here. So, now if you look at that, this is two concepts. If you look at it's a very tiny dust particles when falling down in a very standstill air conditions, that how much of force is acting on that. So, if a dust particles, very tiny dust particles, if it's falling down, there will be the force, weight, the buoyancy force and the drag force. And when it attains this maximum velocity, which we call the terminal velocity, after that it does not change it. So, in that is the conditions when you have a velocity increases the drag force until all the force balance each others, that means net force acting on the body is 0. Then after this velocity attains the maximum velocity, which the terminal velocity. So, that means a smaller dust particles, it will fall on a terminal velocity, terminal velocity. That is the conditions when you have a balance between the buoyancy force, weight and the drag force. So, that means if it is moving with V terminals, the drag force is equal to weight minus buoyancy force. That is what you can easily compute it. What will be the weight, what will be the buoyancy force, depending on the fluid density and the density of the dust particles. So, we can always compute it, what will be the weight, what will be the buoyancy force, you can compute the drag force. There could be a flow separations and all, it also depends on the Reynolds numbers and the roughness. The same way if you look at that when you flow past in aerofoils. So, you will have a positive pressures, there will be a negative pressure difference and there will be friction drags as well as the form drag or drag due to the pressure difference. That is what is happens it. The top of bottom there will be pressure which generate the upward force that tends to lift the wings and the aeroplanes to which connected. That is what if you look at that how the aeroplanes are taking off, how they are operating this the van during the lifting and also the landing conditions, all the lift and drag force concept we generally correlated to look at all the operations what is done by the pilots. So, that is what you can understand it a similar way. Now, let me have a very simple way the frictions and pressure drags. As I said it, the part of drag directly from the wall shear stress, which is called as a skin friction drag, since it is caused by the frictional effect because of the boundary layer formations. There is a part which is directly dependent on the pressure difference, which is the drag force because of pressures. So, sometimes because it depends upon the shape or form of the body, as I said it, a tall building, high rise buildings having rectangular shapes platforms or a circular platforms, it differ it. So, that means all it difference between the form drag, which is depends upon that what type of shape and form of the body. So, we again define it the same way. So, CD frictions and CD pressures. So, the frictions and the CD pressures, it is a difference between the lift that we are talking about a dominancy force component. One is a frictional part, another is a form drag. But the lift and drag force, all components we are considering in the flow directions and another is perpendicular to that. But in this case, we divide it depending upon why it is happening, because of the pressures and because of friction separately. That is the difference between the coefficient of drag coefficients and the coefficient of frictions. Coefficient of frictions talk about because of the frictional effects what is coming it, and this is due to the pressure drags because of form drags as it depends upon the state. So, that is what we define it to. So, as I said that the drag coefficient F d, it has this two component, Okay. FD will have a two component, one will be FD as a frictions, another is FD for the pressure or the form drag. That is what. Now, if you look at one of the very simple examples that how the drag coefficients the CD varies, okay, friction drags and the pressure drags varies it as we change the D by L ratio. Okay. So, D by L ratio, if we are changing it of a flow systems, how this CD of friction drag and pressure drag, and this is what the total drags. So, if you look at that, the total drags comes like this, which gives a, there is a minimum points, the ratio between D and L, where we will have a total drag is the minimum. So, this type of design we consider it when you try to design a object. Now, come back to very common geometries, okay, which is very easy to we have from experiments. But if you look at smooth spheres, okay, and the difference is smooth because there is not much roughness is there. Okay. That is the reason it is a smooth. It is a Reynolds numbers as the CD. So, if you can look at the first part is a linears, then its behaviors like comes like this. Okay. So, beyond this it is a turbulence and there will be the laminar regions. So, if you look at that, the coefficient of drag or drag coefficients, which is really varies between the laminar flow, the creeping flow, the laminar flow, transitions and turbulence, and it has a smooth. So, these are the reasons if you look at then again it decreases. Okay. This is the linear part follows by these parts. Okay. So, this linear part when the flow is laminar, okay, or very creeping less than the Reynolds number 1, less than very less than 1 values, okay, that is called the creeping flow. So, if you can see that, for that we can define for a simple a functions with a Reynolds numbers, okay, that is because it is a linear functions. Okay. So, that is what is define it for a spherical space. The CD is 24 by Reynolds numbers. So, you can ask how did you get these ones. Okay. This is all the experimental study was conducted almost 100 years back to with a simple experiments to find out the drag forces with different Reynolds numbers, and you can find out the CDs. For other cases, we see this functional relationship, how the Reynolds numbers is very similar with the smooth cylinders. Okay. For the smooth cylinders you can have. So, as I was talking about, the CD for a hemispheres, circular case, all no doubt inversely relations with a Reynolds numbers. The higher the Reynolds number, CD value is usually less, but the coefficients, that is what is different. Okay. As you expected it, in case of this type of case, we will have the drag force is less, because that is what we do it. Okay. So, if you look at that, basically what I am to say that you please commonly related to your day to day activities with a drag and lift force, then really you can enjoy these chapters, which is it is a give a knowledge to us that how we can really make it interesting of the fluid mechanics, or how can you use the fluid mechanics for day to day lives, or any engineering subjects. When you try to do it, we can just think it that how lift drag force are happening it, or you can cross reference to look at the standard tables are given in lift and drags in many of test book like Sinzel Simbala or FM White. You can understand it how the drag force are changing it, just observe looking this value of CD. So, as coming back to the creeping flow, it is a very simple things. Okay. when you have a Reynolds region number, that's what is CD is equal to 24 by Reynolds numbers. Okay. So, that means when you have the dust particles, there is no much wind flow, that what will be the flow will have a Reynolds numbers much lesser than the 1 or close to the 1. So, in that case the C you will have a same formula CD rho V square by 2 into area. So, that is what you dynamic pressures multiplied by the frontal area into the CD. So, as this is a 24 by Reynolds numbers, that is what is got it from experiment into the rho V square. So, you know very well that frontal area. So, you can find out what will be the frontal area, that is what is you can for a D surface. Okay. So, as a spheres, so we can get a frontal area phi D square by 4. Okay. Substituting all these Reynolds numbers and all, finally, with a simple equations you will get it V and D. That means, the drag force is a directly proportional to velocity, diameters and the dynamic viscosity of the mediums, okay, in which the dust particles are falling down. Okay. So, you know it, the dynamic viscosity of air also changes with the temperatures, that also you know it. So, that way if you can try to understand it, the dropping of the dust particles, it has the functions of velocity, at what velocity is coming it, and it also depicts that the diameters and the mu value. So, that is what is called Stokes law. It is valid for the dust particles. Not only that, any suspended solid particles in the water also follow the Stokes law. It is very simple law, because it has consider the force components as we know it, and also is considered with the experimentally what is the CD value. That is the relationship between the CD and the Reynolds numbers. More details of the parallel flow as we discuss in the classes, okay, in boundary layers. I am not going more details, but as the object surface, okay, as just a simple way I will just talk about, already we have discussed it that. So, we can have a laminar regions, laminar boundary layers, transitions and turbulent boundary layers. So, that way you can get it a coefficient of frictions variations for laminar and turbulence is a different, which is a functions of the Reynolds number, which is the functions of the Reynolds numbers. It has given these threshold Reynolds numbers, and if you just want to do it total average friction coefficient, then you can have a Cf will be 1 by L, just integrate it Cfx ds. So, you are just integrating the Cf dx values 0 to L, that is what will give you average friction coefficient. So, that way you can always do the integrations for the laminar regions, you can do for the turbulent regions, and you can estimate if a plate is too long, partly turbulent and all, you can do a integration between that. If you find it okay, only the laminar flows happens it, what will be the average flow, or you just assume it okay, it's the laminar flow is not significantly contributing the average friction coefficient, only the turbulent regions you can consider it, which will give it in a function of Reynolds number. Same way, if you are considering there are two laminar as well as the turbulence happening it, so you can do the integrations to estimate what will be the average friction coefficient. So, for more details, if you look it for entire plate, you can have these components as that integrations part. and here is showing it for a smooth and rough plates. That is what you can have put the Reynolds numbers, the CF values, okay, and here is fully roughs and all. This figure is very close to, resembles to Modi chart, same way. The concept is the same as we discuss in Modi charts, and the same way the roughness, Reynolds numbers, and the CF values. Okay, is the average friction coefficients. Okay, similar way the lift forces, you will get it as we discussed earlier. This we can have lift and drag forces, and you can contribute to look at the directions as I thoroughly discussed earlier. And when you look at the lift and drag forces, very short way I can say it, you have to look at where the flow separations happens. Most of the times in engineering we try to avoid the flow separations, because if there is a flow separations, then will be the force due to the pressure difference that form drag will be much more higher. So, that is the reasons we try to avoid to formations of the flow separations. But this is what, so that is the stagnations points, and you can look at how the symmetric, non-symmetrical two-dimensional flow around and aerofoils. So, you can understand it. I think these are the things we discuss more details, but let us come back to two examples, which after this we will be finishing this class. It is a very simple examples of wind tunnel test. The car is moving with 60 miles per hour, okay, and the force frontal area known is, so A is known, the frontal area is known to us, and the velocity is known to us, okay, and the drag force with a simple Pauli arrangement we can estimate it, what is the drag force we are getting it, and so you have to compute it what will be the drag coefficients. So, it is a very simple things, okay. F d is equal to half rho v square dynamic pressures multiplied the frontal area, which is given to us, is equal to C d. I think this is quite easy for us, only you have to know it, what is the density, velocity is given to us, area is also given to us, the drag force is given to it. So, just to substitute these formulas and get it what will be the drag force. Okay. Just to look at the solutions part, it is a simple. First is you have to compute, estimate the density of air for pressure and the temperatures. So, we can get it this, as I have said it, the drag force is this part, as so you just substitute it and rearrange it, you will get it drag C d value, which will be 0.34. Okay. The simple substitution of equations of drag force equation. Second example is quite interesting. It looks like a tennis balls. As I said it, if you talk about cricket ball or tennis balls, all these aerodynamic things we try to understand with a drag force and lift force. Okay. This is a very simple examples of how a tennis ball with a mass of 0.0567 kg, it has the diameter 0.064 and it has speed is about 20.1446. It is a spinning it. Okay. So, this is a 4800 RPM, rotations per minute. Determine if ball will fall or rise under the combined effect of the gravity, the lift during the spinning shortly after being hit at a air at 1 atmospheric pressures and 80° Fahrenheit. Okay. And CL is given to us. Okay. The coefficients of lift is given to us. That means we can find out lift force. Okay. We also know it, the weight. So, if a lift force is more than the weight, then you can easily find out ball will be rise it if the lift force is greater than the weight. Reversely, if the lift force is lesser than the weight, so ball will fall. So, this is very simple cases, but descriptions is written it in terms of tennis balls. It has the mass, it has the diameters which needs for to estimate the frontal area. We have the velocity and you have a spinning speed which is not necessary here, because it is already is given it what is the lift coefficient for the spinning conditions. Okay. So, that is it is given to us. So, that is the reasons you can compute the density, you can compute estimate the kinematic viscosity. So, ball is hit horizontally, thus it could normally fall under the effect of the gravity without a spin, because if you look at the density and the density of mass is given. So, you can compare the density in normal case anyway ball will fall into the gravity, okay, without spin. Spin generates a lift, but ball will raise if the lift is greater than the weight of the ball. That is what I told. Okay. So, you can just look at this. So, we need to compute the lift forces, okay, whereas lift forces again I introduced it is the same things, okay, half rho b squares into the A. So, that is which you know this area and the lift force is coming about 0.161 newtons, but the weight of the balls is coming around 0.556. Okay. So, that way the weight is greater than the lift force. So, ball will fall down. So, okay, no doubt about that. So, ball will fall down. So, that is the reason the spinners try to change the speed of the spinning, so that ball can remains at the risings or the balancing levels. That is what it if you look at the spinners how they work hard, practice hard to make it throw the ball such a way that it remains the spinning conditions or at the lift conditions. Okay. More details of the fluid mechanics and the how biological systems works, how the any sports activities, if really it is a interesting subjects and all, because it is introductory levels. I am not going to that levels, but I tried my level best to give a lot of illustrations, as well as I try to give it a one of the best books in which apart from giving a mathematical treatment to the fluid mechanics, also there is series of illustrations, the figures are there which really give you impressions that we can really learn many things about the fluid mechanics, okay, which day to day lives we can use that, or you can be a best engineers to adopt some of the fluid mechanics knowledge. Okay. With this I am not repeating this coefficient of drag and lift coefficients part as a summary of these lectures, and the thickness and coefficient of frictions. Okay. You with this let me I conclude today lectures with giving really heartfelt thank to all my students who really helped, Mr. Chandan Pradhan, Ketan Nandi, Ridik Kakoti and Lasya Mani Sao. Thank you a lot.